All right, so welcome everybody to Condensed Matter Seminar. Again on Mondays. So thank you very much for coming. We're very happy to have our own professor Guoqing Chang come talk about his work. Guoqing is a non-English professor and also a National Research Foundation fellow. At NTU. He graduated from NUS some small number of years ago, and then he went on to do a very successful postdoc at Princeton with Zaid Hassan. He predicted many new things, in particular in photocurrent and nonlinear responses of these topological wire semi-metals, and also a new class. He kind of pioneered, helped to pioneer a new class of these chiral wire semi-metals. And he'll probably tell us more about it this time round. Guoqing is a theorist. In particular, he's a density functional theory theorist, a very good one, and able to do very good calculations, produce band structures, and produce very interesting response functions. And so, without further ado, let me welcome Guoqing. Thank you very much for this seminar.
Okay, thank you, Justin. So my today's topic is about topological quantum phases and their novel phenomena, mainly focusing on their nonlinear optical responses. And I think in the last week, Professor Chuma has covered some of the talk. Yeah, so because my work has close collaborations with experimental groups, so in my today's presentation, I will also have some work related to the experimental measurements, which is really close to my predictions. Yeah. So let me first briefly introduce what's a topological insulator. So this is the starting of topological physics. So the idea actually brings the mathematical concept. So for example, for the four pictures on the left, in mathematics, if you talk about the geometry, they all belong to different catalogs. However, if you want to study the global structure, which they define the topology. So the left two, they belong to the same topology because there's no hole on there, and for the middle two, they belong to the same topology because if you're counting the holes on the system, they both have one hole. So we bring this idea to the band structures. So in principle, we try to study the quantum wave functions of the system. And for example, here I give the formula of Berry phase, and from which we try to define some topological invariants, which usually are integers. These integers can give us a definition of the topology of the system. For the example for insulator, where the bulk bands are fully gapped, so it's possible there is some surface in between them. So if we try to define the topology of these insulators, we can find some trivial insulators, like on the left one, where you have even number of surfaces pass through the gap, and these states can be easily moved away if you try to add perturbations on the system. However, for topological surface state, you will only have one old number of H state or surface state connecting the conduction and valence bands, and you can never be able to move them away unless you fully destroy the topology. So the way to create the topologies is just this called, usually people think about the creation of topology by the process of band inversion. So we usually start from conventional or trivial insulators, and the conduction band and valence band, they can touch and invert in energy and momentum space. So this process, the top of the bands go below, and as a result, there will be some topological surface states in the gap. So this process is just like digging a holes on the what we have seen in the previous slides. So this is the idea for topological insulator. So, but there should be another idea. If these two bands invert, the system can still become gapless, which we call it semi-metal or metal. So in this way, we are supposed to define the topology of these metal phases. So the most typical example is the wire semi-metals phases. So let's start from the Dirac equation. So we can try to make the formula to be mass term to be 0, therefore we will get the massless Dirac fermions. So now we have, in this formula, we have both all the Pauling matrices sigma x, sigma y, and sigma z in 3D system. So now if we look at the two diagonal blocks, there you can see each block have the same formula, but only difference is the sign in front of. So each particle we can define as a new particle, which is called wire fermions. And this signs in front of it actually determine the chirality or the Chern number of each wire fermions. So how do we define the topology of wire fermions? We try to calculate the net buried flux. So each wire node is a twofold degeneracy in energy momentum space. So if we try to plot the buried curvature around this wire node, you can see they behave like a source or sink of the buried curvature. So therefore, if you use any 2D manifold to enclose one of the wire node, you calculate net buried flux. You will, using the Gaussian's law, you will see this is a quantized value. It's a integers. So we define this as the Chern number of these wire nodes. Wire nodes can be positive or negative, so they always appear in pairs because the net Chern number for this system should be 0. So with this simple picture, now we assume we have two wire nodes in the momentum space. Now in between them, we define a 2D subsystem. So the buried curvature will flow from the left to the right. And if you count the net Chern number through this plan, you will see it will be a quantized value. So as a result, this 2D subsystem actually can be analog of the 2D norm source system, where you will see a chiral edge mode connecting the conduction and valence bands. So if your Fermi level is here, so you will have a point like Fermi surface here. So this is always true for all the 2D plane in between the two wire nodes. So therefore, you will, at the constant energy contour, you will extend the surface state in between the two wire nodes, which will form an open surface state, connect two wire nodes, which have opposite Chern number. So in 3D picture, you will here is a distribution of the wire cone and the fermionic surface states. This red and blue are the linear cone of the wire fermions, and this red and blue actually indicate the Chern number of this wire node or each band. And this yellow surface are the fermionic surface states which connect these two wire nodes. If you only look at one surface, look at one edge, it will just be some line which are arc-like features. So with this idea, people started searching for wires and metal candidates. So the first one that was realized in experiments is TS family. So this is central symmetric material. So which a non-central symmetric material where we cannot define the inversion center of the wire fermions. So sorry, previously I didn't mention that. So to make the two wire fermions separate here, because in this equation, these two wire fermions are still spin degenerate. At one point, it's like Dirac fermion. So to make them separate in energy in momentum space, we need to break the spin degeneracy, which requires us to either break the inversion symmetry or time reversal symmetry. So this TS family actually is an example where we break the inversion symmetry of the crystal. So here I plot the band structure. We can see that around the Fermi level, it's a symmetrical, and we can clearly see the band inversion along sigma and sigma 1 pass. After we turn on SOC, the spin coupling into consideration, these crossings will hybridize and open band gaps. So if you look at the fully high symmetry lines, it will become an insulator. However, this is not true because the wire nodes are actually at the generic points of the momentum space. So we need to search the Hilbert zone to locate the wire nodes. Here is, for simplicity, I will give this a cartoon to illustrate the distribution of wire nodes in the momentum space. So they are not at any high symmetry lines or high symmetry points. So this is the projection into 001 surface, and this white and black actually indicate the Chern number of the wire fermions, and these numbers here actually are the total charge projected at this point. So if we choose plot the bulk bands along this direction, we will see the EK dispersion, which have the linear dispersion and almost degenerate here at the Fermi level. So this is the RPI's measurement, which directly visualize the band structures of the crystal. This intensity, this region with low intensity, you tells us no states. This one with high intensity actually tells us there is some states. So these are the linear cones, and these are degeneracy points. So these are the APAS measured box states. So to further demonstrate these are like wire fermions, not like the Dirac fermions in graphene, we need to further visualize the surface state, which is the fermions we discussed. So on the right panel, we show the surface state. You can see where the APAS observe these dots actually are the Fermi surface of these Y nodes. These orange dots are the bulk nodes. So these green states with high intensity here actually are the Fermi arc surface states. You can see there are two arc feature. They terminate at these two nodes. So these are the direct observation of the Fermi arc surface states. And here I didn't show the my predictions. Actually, it's perfect match with what they observed. So this was what people study Y-symmetry previously. They're trying to locate these Y nodes at generic points of the momentum space, but this is really time-consuming and heavy in calculations and also time in experiments. So inspired by this idea, so I'm trying to think about whether we can try to locate the Y nodes at some high symmetry points. So the first thing that comes to my mind is the Cramer's theorem. So according to the Cramer's theorem, if you have a system with magnetic, which is non-magnetic, which with preserved time reversal symmetry, all the time reversal invariant points are supposed to be the twofold, at least twofold degenerate. So now, if we break the inversion symmetry, then the spin degeneracy at the generic points will be lifted, and the only remaining degeneracy will be at the time reversal invariant points, as indicated here. So if we look at the band structure here, there will be twofold degeneracy with the linear crossing. If you only look at this path, so this seems to indicate us this is a wire fermion. So can we conclude that all the time reversal invariant points at the inversion breaking crystals or non-central symmetric crystals, these nodes are the wire fermions? No, we need to exclude another symmetry which we define as the middle plane. So assuming now we have a middle plane, according to the knowledge we obtained before, the middle plane will flip the Berry curvature on the two sides. So in other words, if you have a middle plane, you have also a wire fermion. On the two sides of the middle plane, the two wire nodes will have opposite chirality. As a result, if you try to move these two wire nodes into the middle plane, the opposite Chang number they will annihilate. And as a result, the net Chang number that is allowed on any middle will be zero, which means fermions is not forbidden on the middle plane. So considering inversion breaking crystals with mirror symmetries, with mirror, this mirror pass through the gamma for sure, and as a result, these points you cannot be wire fermions. So I do check the band structures along the other paths, so it will no longer be like these crossings. Instead, it will be, you will say that these two bands will become degenerate again. So from this test, we give a proposal that for these points to be Y nodes, we have to break both inversion symmetry and the mirror symmetries. So now we need to have a comprehensive study. So what are the crystals we have if we break the inversion symmetries and the mirror plane? This is the chiral crystal. Actually, in three-dimensional system, around 65 chiral space groups are defined, which is almost 1/3 of the total 3D space groups. So these materials in the chiral space group, they have well-defined handedness, which we can define the left hand and right hand. So because they're lacking on mirror plane, so if you apply a mirror symmetry on this crystal, you will change the original handedness to the other side. For example, if you have a left-handed crystal, you apply a mirror operations, you will change the crystal from the left-handed to the right-handed. So this is the structural chirality in real space. If you still remember the definition of wire fermions, actually they are also the chirality in momentum space, because we define different Chang number or different charge in the momentum space. So now we have two chirality, the structural chirality in real space and the topological chirality in momentum space. So it's a very interesting question for us to answer whether there is a universal link between these two chirality in real space and in momentum space. And after our comprehensive study, we found there's this universal link. So this is a summary of what we discovered. So first of all, let's think about a symmetric chiral space group. This is the most direct case. We use little group theory and point group theory. We found that all the cross these time reversing invariant points actually they are the Cremer's Y nodes with well-defined Chang numbers. So this is one of the example. Here I label this Chang Y fermions at the time reversal event points, and these colors represents the different Chang number. So the story for the symmetric chiral space group quite simple. All the time reversal event points, they are the Y nodes. For the non-symmetric one, the story will be a little bit complicated. This is what example I show here. So for the non-symmetric chiral space group, which means you have some screw rotation symmetries. And the screw rotation is a direct rotation plus a translation of fraction of the Brillouin zone, for example, half of the Brillouin zone. So this sometimes can introduce actual degeneracy on the Brillouin zone boundary. Of course, if you don't have any actual degeneracy, it will be same as a symmetric chiral space group. If you have this actual degeneration on the boundary, here is an example. At gamma point, it will not be affected by the non-symmetric symmetries. So it will still be like these Y nodes with well-defined Chang numbers. However, on the boundary, for example, this is space group 19, you will see all the Kx, Ky, Kd, they are twofold degenerated. So which will form a fully degenerate nodal box on the whole Brillouin zone. And if you can see, if you in this material, if you search the Y nodes in the momentum space, you will see only these gamma points are crossings, and also this boundary. There are no other crossings in the Brillouin zone. So if your Chang number have to be natural, which means this nodal box have to contain the Chang number of which are opposite to the charge in the gamma point, so that you will have the natural charge in the whole system. So we found that indeed this nodal box actually has a Chang number where we define the chiral nodal box. So this is for the two class. So besides the twofold degeneracy, we found that actually the multifold fermions can also contain non-trivial Chang number. So we found that in cubic chiral space group, actually it doesn't matter whether this is a symmetric or non-symmetric. In previous people found that the non-symmetric crystals can have the non-multifold degeneracy with a Chang number, but we found that this is not necessary to have this non-symmetric symmetries. Just the cubic chiral crystal is enough. And in principle, we found there are three new kind of crossings: threefold, fourfold, and sixfold. So this multifold chiral fermions actually is a generalization of the twofold Y fermions, because each band we can still define the Chang number. So for example, if you have a threefold Y fermions, so we can have two gaps in between them. Therefore, we can define the Chang number of each band gaps. So therefore, to fully describe the topology of these threefold fermions, we need at least two integers. Similarly, for the fourfold Y fermions, we need 3 integers, and sixfold Y fermions, we need 5 integers. These integers are defined by the summation of all the bands below the gap. So, and this number will be very important for us to further counting the number of Fermi arcs and the optical response. I will discuss it later. So here with this cartoon all present here, we found that all the point-like or nodal-like degeneracy in the chiral space group, they actually are all topological chiral fermions. So as a result, in conclusion, we can see we found a universal link between the real space chirality and momentum space chirality. So follow this idea, we start finding the material candidates to best realize our idea. So this IHSI family is the best material candidates we have found ever. So it's a very simple two component materials. This is cross structure, which is Chiral. And in the middle, I plot the band structure of IHSI and COSI, I ignore this spin orbital coupling. You can see there is a three-fold crossings at gamma points with linear crossing here and almost flat bands in the middle, and another four-fold crossings at the R point, and a small pocket of M. So this one can be easily moved away if you do the electron doping. So if you look at the Fermi surface around 200 milleV of this system, you will see there is a positive Chern number at gamma point and negative Chern number at the corner R. So this is a very clean band structure which have the topology. So here I have a comparison of this IHSI with TS. You can see they have the separation of Y nodes in IHSI is at least one order larger than TS, and it had much less Y nodes and much higher Chern numbers. And the most important of all, we have much larger topological non-trivial window. So how do we understand the topological non-trivial window? So previously we mentioned that we need to create Y nodes by the band inversion. So this is the way to create the conventional Y-side metal. So the degree of the topological non-trivial window actually is fully determined by the degree of band inversion. So the way to understand is this. So we have two Lifshitz transition here, this top and this bottom. So if your Fermi level is in between them, if you cut here, if you look at the Fermi surface, you will have two isolated Fermi surface, which include these two Y nodes inside. So where you can distinguish the topology in momentum space. However, if you go beyond this Lifshitz transition, like the energy E2 here, these two pockets, actually, they will merge into one. As a result, you will have two Chern number combined together. If you look at the Fermi surface, this net Chern number of this Fermi surface is there. So in this way, actually, there's almost no difference between the Weyl and Dirac fermions because you cannot distinguish the charge in momentum space. So we define this window as a topological window where we can really detect the non-trivial topology of the Weyl fermions. So for comparison, we can see the IHSI, because we don't have the band inversion, so the separation of these two nodes actually almost determined by the original dispersion. This can be an order of 1 eV. And in conventional Y-side metals, this window actually is only around the order of 10 millieV for most materials. So TS is already the best one, which is still less than 100 millieV. And another thing is energy difference. So if you have a mirror plane, so mirror symmetries will translate the Y nodes to the mirror partner. They have opposite Chern number, but they have to locate at the same energy. However, for the chiral crystal, these two Y nodes, they can locate at different energy. This energy difference is very important for the further applications in the magnetic response or optical response. So let me first show the RPAS measurements. So this is a direct measurement by photo emission. So where you can see on the left panel is the crossings of the Y nodes, the chiral fermions at R point. At R point, you can this at R point is supposed to be a four-fold fermions, but due to the limited resolution, we can only see the degeneracy points there. So therefore, to fully demonstrate this topology, we need to see the surface states. So the middle panel shows the measurement of the surface intensity at the Fermi level. So these high intensity states actually are the states where we suppose to have electrons, while the very dim region where we are supposed to have no electrons there. So we can see there's a big pocket at gamma and a small pocket at M, and also a trivial pocket at X bar or Y bar. So in between them, there is a very narrow states connecting this M bar and gamma bar. So actually, these are the Fermi-Axis states according to my calculations here. This is the long Fermi-Axis states connecting this gamma bar and M bar. So to fully demonstrate the topology of these states in experiments, we need to measure the energy dispersion. So for example, we cut through this line, we check the EK dispersion. You can see the only states that cross the Fermi level are these states, which we define as the Fermi-Axis states, the chiral H mode. While there is no other box states, around the Fermi level. So all the box states are actually here is around 100 MeV below the Fermi level. So there's other box states above the Fermi level. So these are actually the topological chiral H mode connecting the conduction and valence bands. So besides IHSI, people have independently observed this chiral H mode in the other materials, including the COSI and ALPT. So although the band structures are, the details of the band structures are different, but the topology are still the same. So you can see this long Fermi axis connecting the center and the corner of the brain zone. Similarly here, you can see this is the corner, this is the center. We see this Fermi axis connecting all the way to the center, then go back to the corner. So this topological chiral state can only be realized in the electronic system because it's symmetry related to topology. Therefore, in principle, you can realize in other system. For example, Weiler, they realized this one in the acoustic metal materials. So they design such a chiral structures which can allow this topology. This is their direct measurements. They can see their data is more cleaner than the electronic system, where they only have this Fermi-Axis states connect these two pockets, one at the center, one at the corner. And they have further realized the negative refractions in the system. So this is when you have two chiral crystals and try to combine them into a system, and on the boundary, on the two sides of this is the boundary of the system. On the two sides, you will have two chiral crystals with different shape of Fermi arcs. And because the Fermi arcs is open surface states, we can realize these negative refractions, and there's no states allow the reflections. So the reflections are forbidden, and this is the only way this wave can pass through the boundary. So it's the negative refractions. So now let's come back to the basic topology of multifold chiral fermions. So previously we mentioned that we see the linear cone, we see the chiral H mode connecting the conduction and valence bands. But this is actually the physics of wire fermions. But for the multifold chiral fermions, we have more than two bands. As a result, we will have more than one gap. So if, as I have mentioned, for each gap, we are supposed to define the topology. So if you check the EK dispersion, similarly cut away, slightly away from the wire node, you are supposed to say the Fermi-Axis states in each band gaps. So previous work, they only demonstrate this IHSI family or the other crystals, they are ideal wire-like crystals, but they didn't really demonstrate the multifold topology. So let's relook at the band structure here. You can see this R point is below the Fermi level. However, the splitting here is very small. So within the experimental resolution, we cannot really directly visualize this multifold crossing. The separation in gamma point is large enough. However, if you see the Fermi level, these crossings actually are slightly above the Fermi level. So the R pass can only see the states below the Fermi level. And also due to the sample in experiments there, this sample is slightly hot doped. So which will push this node further away from the Fermi level. That is why people didn't really directly see the crossings there. Therefore, to really observe this one, so I propose we should do the electron doping on the system. And in IHSI, I found that we can do nickel doping on the crystal without change the topology, and the system still remain as non-magnetic. So this is our recent result. So this is the band structures. If we do the electron doping, you can see the crossings are more below the Fermi level. And this is the direct upper measurements along cutting through these multifold chiral fermions along different paths. We can clearly observe 3 branches of the cones. They meet at this location, which is around 200 millieV below the Fermi level in both K paths. Of course, due to the resolution, we cannot fully say this is really degenerate or not. So we try to cut slightly away from these nodes. So you can see this in this region, we can clearly see these 3 bands are separated. We can clearly define the gaps in between these 3 bands. So this is the good chance these are the degeneracy points. So we can also look at these constant contours at different energies. So you can see above from 0 to 200 millieV, this is the Fermi surface from the up cone. Below 200 millieV, we're supposed to have observed 2 Fermi pockets. One is from the middle cone, the black one. The other one is from the lower cone, the blue one. So these signatures are also consistently observed in the direct experimental measurements. So this is the up cone Fermi pockets, and this is the lower cone of the Fermi pockets, and this most large Fermi contours are from the middle bands. Again, to fully demonstrate the topology there, we need to observe the topological surface state. So here is the direct measurements of this topological boundary state. So we zoom in on this region, we can see 2 sets of arc-like feature. The 2 very short arcs in the center and the 2 long arcs on the boundary. And if you check the EK dispersion, we can clearly see there are 2 chiral edge modes which are propagating in the same direction, but they are located at different energies. Therefore, to demonstrate this one of Fermi arcs, we need to check the bulk boundary correspondence. So this is the direct measurement of the bulk states, and we put this surface state measurement on top of the bulk measurements. We can see on the constant energy contours, this arc structure are within this pockets from the middle bands and outside the pockets from the lower bands. And this arc structure are actually outside the middle pockets and connect all the way to the corner. So if we check the EK dispersion, we can see this the bands. This is the lower bands, and this is the middle bands. The up bands is above the Fermi level, cannot see it, but you can see these are actually connecting this middle and lower bands, and this Fermi arc actually connecting the middle band and all the way up to the higher bands. So with these measurements, we fully demonstrate the topology of the multifold chiral fermions. So now I want to show the interesting physics of these Fermi arcs further. So in the 2016, Liang Fu, they mentioned that the Fermi arc surface state actually is a complete Raman surface state, which exhibit these helical structures. And we indeed observe this one directly in experimental measurements. So for example, if we choose a constant loop and check the location of the Fermi arcs across this loop at different energies and trace these points, you can see with the changing of the binding energy, this location of Fermi arcs actually are moving in energy. So for gamma points, it rotates. If you increase the energy, you can see this Fermi arcs points are rotate anti-clockwise. And for M points, we also choose a loop here. You can see these Fermi arcs actually rotate clockwise. So this is the 3D structure, how will the Fermi arc rotate in energy momentum space. This rotating structure actually can induce many very interesting states, which I define as Fermi arc Van Hoffs. So let's look at the mechanism. So we start from this cartoon here. We have the Fermi arcs connecting gamma and the corner. So this Fermi arc will rotate anti-clockwise around gamma, rotate clockwise around M. So with the increasing of the energy, these two Fermi arcs, they are supposed to move close to each other. In some point, they are supposed to meet at the Y bar, actually, because this and this actually, they are time reversal partner of each other. So this and time reversal partner, and you need to translate for a Hopf-link zone from here to here. So if they meet, they must meet at the Y bar. But this spiral structure will keep on rotating. They will move away from each other, where we will see the Fermi arc connection will be swept, and they will further move away. So if we look at this structure here, from here to here, this is the typical constant energy contour feature for the saddle point or the Van Hoff singularity points. So I propose to directly measure this Van Hoff singularity points in this class of material by do electron doping of the crystal. So this is the direct measurement. So you can see with the increasing of the Fermi level, this Fermi arc states, they are become moving closer to the Y bar. And unfortunately, this doping in this material is still not enough, but the trend is still there. If you look at the comparison of my calculations, this is the Van Hoff singular point. This is below Van Hoff. They are moving close to each other and meet. So above the Van Hoff, they will be further move away in the other direction. So this is the EK dispersion at Y bar. You can see we see these states, electron-like states, Hall-like pockets, the band structure around Y bar along KA direction. In KY direction, there is no such a band structure. Actually, the band is above Fermi level. So it will be an electron-like path. So in the further work, we are supposed to do further electron doping to reach this Van Hoff. Although we didn't really observe this saddle point there, but we have observed another type of Van Hoff in this class material. So this also originates from the spiral structure of the Fermi arc, but now we only need one Fermi arc. So because this Fermi arc is very long, so as a result, the Fermi velocity at different locations of the Fermi arc, they are not homogeneous. So for example, if you look at here and here, they can rotate very quickly. But at this location, the spiral structure actually moving very slowly. As a result, you will create a kink structure on the Fermi arc surface. As a result, these 2 points actually, they will move towards each other and create another Van Hoff singularity, which are defined as the intra-Fermi arc Van Hoff, and they will further move away from each other and forming a new Van Hoff singularities. So we indeed observe such a very interesting kink structure from the Fermi arc states. So to further directly see this Van Hoff, we need, according to the calculations, we need to lower the energy. So we do the measurements by lowering the photon energy. So at the Fermi level, you can see these states, this 2 points, they are moving close to each other and meet some points. If we do further away, they will move further away from each other. So to demonstrate this one, we plot EK dispersion pass through this potential Van Hoff singularity points. You can see along K1 direction, we see a Hall-like band structure. Along K2 direction, we see a electron-like structure. So this actually a direct observation of this saddle point structure from this Van Hoff singularity points. So this class of material have great tunability because we can do the nickel doping or to make the electron dop, or do the Fe doping to make it Hall doped. And this doping, we found that it will not change the band structure and will not change the magnetization of the system. So it's just a pure simple leaving or decreasing or increasing of the Fermi level. So here I give an estimation of to which level we can move this Fermi level exact at the Van Hoff. So in this system, we are supposed to realize both type 1 Van Hoff at the time reversal invariant points and type 2 Van Hoff at generic points of momentum space. According to previous theory, people say that the type 2 Van Hoff prefer a P-wave superconducting. So in the future, if we can really move this Van Hoff to this node, maybe we can realize, because this Van Hoff singularity points are peak in dense of states, therefore can induce many instability of the band structure. For example, like the magnetization, charge density wave, or superconductors. So if we realize superconducting states, maybe we can realize the topological superconducting states with the Majorana boundary states. So this is about the Van Hoff singularity of fermions. Now let me introduce the nonlinear optical response. So in principle, we can, in general, this is a formula. This is a very general formula if you detect the photocurrent on crystal. So this is the first term is a linear term, which means if you apply a direct electric field, you can have the current. The second term actually is a second order response, is a nonlinear response. So this actual response, when the case where you apply a laser, a polarized laser, for example, if you apply a linear polarization laser or apply a circular polarization laser on a crystals, according to this formula, if your crystal is lacking of inversion symmetry, you can have the DC current, which we can directly detect here. So the current induced from the linear laser is called shift current. The current induced by the circular polarized laser we define as the injection current. In the early days, people trying to study this CPG or shift LPG, mostly in the ferroelectric materials or usually the semiconductors, because they are supposed to have much larger photocurrents. Now my attention will focusing on these semi metals, and especially the wire semi metals, because we can induce the topological photocurrents. So we're starting from the simple circular Photogrammetric effect. So where we have this formula, J will be the tau is the relaxation time times the matrix, which is matrix define how the photocurrent will propagate. Then this is the electrical component of the laser. So people have found that if you look at the diagonal term of this matrix and do the trace of this matrix, it will be, if you apply this formula to a wire fermion, this will be proportional to the integration of the buried flux. So if you have a wire node, this integration will be the Chang number. So the total Chang number or the total photocurrent actually is a direct measurement of the net Chang number. So your photocurrent is proportional to the Chang number. So however, if you have a positive wire fermions, your photocurrent will be positive. Photocurrent will move in this direction. However, if you have a negative wire fermions, your photocurrents will in opposite direction because the Chang number from here to here are different. However, because I have mentioned that wire fermions, they always appear in pairs, right? So the result, if you have a wire semi metal, you expect this photocurrent and this photocurrent will cancel with each other. So how can we make full use of this photocurrent from the wire fermions? According to the proposal of John Moore, they found that they can, if we try to move one wire node above the Fermi level, the other one below the Fermi level. So your Fermi level will be in between them. So you will see this wire node will be occupied. This wire node will be empty. So if you choose some frequency, as indicated here, you can pump electrons from here to here and inject the photocurrents. However, for the lower wire cone, because both bands, both cones are fully occupied, so the optical absorption are forbidden. In this way, you can have the photocurrents induced by one wire node only, which is, as a result, you can have the photocurrent which is proportional to the Chang number. And if you refer to my topological crystal theorem, actually to realize this energy difference, we really need make full use of the topological crystal instead of the previous crystal where we have the mirror symmetries. So I further generalize this theory from two-band system to multi-band system. So for example, this is a 4-fold chiral fermions. So I do the simulation of the photocurrents, and I found that the photocurrent is proportional to the Chang number of this gap in between. Here is 4. You can see this is a blue curve, and you can see a plateau of photocurrents is realized, and which is proportional to the Chang number. And here I have a comparison of conventional two-fold wire fermions, which is the black curve. You can see this is a plateau predicted before, which should be equal to 1 for the standard wire cone. So in principle, we found that as long as you have chiral fermions, we are supposed to realize this multifold. We are supposed to have this topological photocurrent. And my prediction of the IHSI material provide the ideal material platform to realize this interesting phenomenon. So this is recent experimental measurements from two groups. One is from Orenstein group from Berkeley. The other one is Liang Wu's group from Pennsylvania. So they measured on different compounds. They both observed the plateau of shift current. And this plateau will decrease rapidly when you increasing the photo energy, because at this plateau, you only excite the electron in one wire fermion. However, if you further increase in the Fermi level, the electrons can also be excited from the lower wire cone. This photocurrent, they will cancel with each other. As a result, they will vanish to 0. So at this stage, they at least observe a plateau at this photocurrent, but they have not fully demonstrated this plateau is really equal to the Chang number. So this is what are supposed to do further in the experiment. So this is all this we are talking about the bulk photocurrents. So how about the surface? So as I mentioned, this class of material have a very large surface state. So we cannot just ignore the effect from the surface. So here I actually look at the EK dispersion along this red line. You can see we see this fermionic surface state connecting the conduction and valence bands. Interestingly, I observe, you can see there is a fermionic state below the Fermi level. There is also a fermionic surface state above the Fermi level. In this way, we can excite the electron from here to here. So the optical transition is allowed, which seems tells me we can using fermionics to realize the photocurrents. And the reason why we can have this transition is also due to the spiral structure of the fermionics. So here is the cartoon or the calculation to explain this mechanism. So for example, this is if you zoom in to the endpoint. So I label two sets of fermionics, 1 and 2. With the increasing of energy, you can see these fermionics are rotating clockwise. So from 200 millieV below the Fermi level to 200 millieV or 400 millieV above the Fermi level, you can see the fermionic 1 and 2, they swap position due to the spiral structure, which allows us to translate electron from fermionic 1 to fermionic 2. Now we know there's an optical channel which allow us to make full use of this photocurrent. Then we need to think about how can we measure the photocurrent from the fermionics and distinguish it from the bulk. So we need to fully utilize the crystalline symmetry. So this class of material have the screw rotation symmetry S2X, S2Y, and S2Z, which is a rotation plus a translation. And due to this translation, due to this rotation symmetry, it will fully cancel the in-plane photocurrent. For example, if I plot the light absorption, so the plus and minus indicate the right and left circular polarization, the light absorptions. So this is the intensity plot. You can see, due to the rotation symmetries, this blue spots will rotate to this location due to the C2 rotation, S2 rotation. As a result, you will excite both sides of the wire cone, and which will induce the photocurrents in opposite direction, so that the in-plane photocurrent will be fully canceled. As a result, if you apply laser on the sample, your photocurrents, the bulk photocurrents will be fully parallel to the laser direction. However, if you apply this to the surface, because of this translation will all be broken on the boundary. Therefore, this in-plane photocurrents will be allowed on the surface state. So from here to here, you can see this distribution of light absorption are fully different from the bulk. Using this cartoon, we can say we can only excite one side of the Fermi arc structure and inject a net photocurrents which in plane of the surface. So in this way, we using the crystalline symmetry to fully disentangle the surface and bulk photocurrents. So this makes us to measure the surface and bulk photocurrents separately. This is very important because the surface photocurrents actually are only due to the state on the boundary, right? So the atoms there are actually very small. However, if in the bulk material you have very thick, inside there will be thousands of atoms. Each atom will contribute to the photocurrents. As a result, your bulk photocurrent usually will be at least one order or even two orders larger than the surface photocurrent in a bulk material. So with this mechanism, we can fully distinguish the surface and bulk contribution. We can directly visualize or detect the surface photocurrent in a bulk material. So I further generalize this my theory to other cubic chiral space group and indicate which class of material we can detect the surface photocurrents, which class of material we can only detect the bulk photocurrents. So here, the left panel is my simulation of the surface photocurrents in the IHSI material. So the Berkeley, they start the measurements, and these dots are their direct measurements. You can see this photocurrent actually have the shape is almost consistent with my measurements. But the only difference is seems that the measurements is shifted in the frequency of the laser. So to explain this one, I look at the band structures with HSE. So previously we didn't include HSE in the calculation. If we include HSE in the band structure calculation, we find that the topology is still the same. The overall band structures are still the same. But the only difference is seems that there is a 1.25 scale of the band structure in energy. So if we take this band scale into my calculations and plot my calculation on top of the measurements, you can see this matches quite well. The peak position for this x direction photocurrents match well. Also, the peak position for this y direction photocurrents. You can see this is the top of the peak. This is the bottom of the minimum peak in the opposite direction. So this seems to tell us the real band structure with material in the future. We need to consider the HSE effect. So besides the topological chiral crystal, where we in the previous in the last slides, I'm all talking about the topological chiral crystal where we exclude the mirror plane. However, the mirror plane itself is interesting if you try to use it on other materials. For example, if you have a mirror plane, the mirror plane will allow the opposite mirror eigenvalue. So if you have two bands on the mirror opposite mirror eigenvalue, and if you let these two bands cross with each other, they can become degenerate due to the opposite mirror eigenvalue, forming a loop structure. This loop structure, although it's the topology different from wire fermions, it's still we can still define the topology in other way. We can define the widening number of a loop, so which means you use any path includes one part of the loop and circle around this original nodal loop, and you can calculate the widening number. This widening number will always be a quantized value, a pi or minus pi. This is quite similar to what people have studied in graphene. So as a result, we will expect to see the flat bands inside this loop, forming a state called the drum-head surface state. So this is they have been intensive study of this nodal loop, topological nodal loop structure. So I will not discuss them today. Now let's extend this theory further. So because if you have one mirror plane, you can have one loop. If you have another one, you will have another loop. So in this way, we can create more than one loop. For example, if we have two loops, now these two loops can have very interesting structure. For example, this is a conventional one. These two loops are further away from each other. However, mathematically, we can also have this loop. They pass through the center of each other, forming the Hopf-link structure. So I found the theorem to explain how can we change the conventional loop into a Hopf-link structure. So I built the model which requires to have 4 bands at least, and the main idea is that this black loop and this red loop, if they look at the bands, they will have the same mirror eigenvalue in this plane. For example, for the black loop, they will have same mirror eigenvalue on this blue plane. They will have an opposite mirror eigenvalue on the green plane. So similarly for the red one, they will have the opposite mirror eigenvalue in the plane where it stays, but the same mirror eigenvalue on the other plane. So in this mechanism, we can smoothly change these conventional rings into the Hopf-link structures. However, there is also another link structure where these two rings, they touch at one point. This is called nodal chain. So I found that this nodal chain is simpler because we only need 2 bands. And these 2 bands just need to have opposite mirror eigenvalue in both planes. So in this way, we will have this stable, robust nodal chain structure. So with this idea, we can say that if we have more than 6 bands, we can realize both nodal chains and the Hopf-link structure in one system. And from this idea, I applied to the Guoqing, the CO2 materials. And this system have many mirror planes. You can clearly see from the band structure, from the crystal structure. And here, this is a ferromagnetic materials. And this is spin down state, this is spin up state. Now I focus on the spin up states, where this is all the band crossings we observed in the momentum, in the space. We have 3 types of loop: the blue, red, and yellow. So this is not easy to visualize if you only look at within the Brillouin zone. However, if we look at out of one Brillouin zone, you can see this yellow loop actually forming the Hopf-link structure, and this blue loop and the red loop, they're forming this outer chains, and this blue one and the yellow one, they form the inner chain. So the whole band crossings here actually are the combination of all kinds of fundamental link structures, forming the complex neural network. This is just like building Lego, where you can put all these components together, forming a complex structure. So this is a direct experimental measurement. So people say this you can see this is this intense states actually are the nodal loops they observed. These are consistent with my measurements. And by checking the EK dispersion, for example, you choose this path, you can see there is a clear linear crossings, which are Guoqing, as indicated by the white dots. And in between, there is a state connecting these linear cone, which are actually the Drumhead substates. And further work, people found that this nodal loop structure in this system contribute to giant enormous Hall effect of this system. And if you put this material and compare with other materials that people have known before, you can see it exhibits much larger enormous Hall effect than the conventional materials. So that's for the loop structure. So we also have some study of the topological Chiral. So yeah.
Hi, Guoqing. I think it's already 11:01. I wonder, maybe we should try wrap up sometime.
Yeah. So yeah, I think that's all for my talk. Thank you.
Oh, great, fantastic. So thanks very much for this, very extensive talk, with lots of results. Let's maybe have some questions. We have lots of people here, so maybe some people might have some questions. Yeah. So Itong, please unmute yourself.
Yeah. Hi. Thanks for the talk. So you said something about using Fermi arcs to create Van Hove singularities.
Yeah.
That went by a little bit fast, but what do you expect this kinds of Van Hove singularities to enable that you couldn't do with other kinds of Van Hove singularities that don't involve Fermi arcs, which are pretty easy to create?
So actually, we'll actually raise another question, because we know the topological states are robust. For example, the wire fermions are robust against perturbations. However, if you have a Van Hove singularity on the Fermi arc substates, this actually induces insensibility.
But to create this Van Hove singularity, you have to fine tune, no?
Yeah,
because the Fermi arcs don't have to meet, so there should be no special robustness in there.
So if we fine tune the familiar wall to exactly the location of the Van Hove, so we expect to induce insensibility on the surface. Maybe, for example, if make the surface become magnetic. For example, if you have a wire metal in the bulk, the surface become magnetic. How will the magnetization affect the bulk wire fermion is one thing. And also, for example, if the surface state will become superconducting, then whether it's possible that the approximate effect can induce the superconducting states into the bulk, and we will have superconducting wires and metal, and whether we can realize the Majorana or some topological superconducting nodes.
Okay.
Yeah.
Sorry, but maybe my question was more like, why do you need Fermi arcs to do this? Because you could create Van Hove singularities in kind of standard ways. Would you be able to also see this Fermi arc instabilities using normal Van Hove singularities, or is there something special about the Fermi arc that allows you to do this?
So for the normal Van Hove, but one typical question is, because here you can see in our case we realize this type 2 Van Hove. So this is I did another theorem that say that if you have type 1 Van Hove, you will prefer the S wave superconducting. However, if you have type 2 Van Hove, theoretically this Van Hove, if it becomes superconducting, it will prefer the P wave superconducting. So in this way, it will have much larger chance to realize topological superconducting states. Yeah.
Thanks.
Yeah. Thank you.
More questions? Shenging has a question.
Yes. Hi, Prof. Chang. Thank you for a very illuminating talk. I have a question regarding this novel Hopf-link structure. You mentioned that we can use the nonlinear optical response to probe the Berry curvature of wild node. I'm wondering, this kind of nodal link structure, do you think there will be any interesting nonlinear optical responses related to this?
Yes, so I think it deserves the study further. So because currently I didn't see a comprehensive study of the nonlinear optical response due to this link structure. And this is mostly because most of material found there have very complex structures. And in other words, if you have a node, most nodal links actually they are metals, or they're quite metal comparing to wires and metal. So the story will be complicated, but it deserves, it's very interesting to study if you play with the toy model to see if you only have a simple link, what is a photocurrent, and whether this photocurrent can be quantized. I don't know. It deserves attention, but your model have to break the inversion symmetry. This is the initial condition you need to consider. Yeah.
Okay, I see. Thank you. Actually, I have another. Oh, sorry. Okay, I have another question regarding the quantized CPG for multifold while node. In the experimental measurement, it seems that okay. I have maybe it's a very stupid question, but why does it seems that the current will increase when we increase from a very small photon energy to the plateau? I'm wondering why is that so? Is there an explanation?
You mean here?
Yes.
I think this is theoretically it's supposed to be all the way to the low frequency. So yeah, here I probably, according to my current understanding, this is because the Fermi level of this material is not at the right position.
Okay.
So if we really want to do, say, a further plateau, we need to do either electron doping or hot doping of this class material. So I have some DFT results which show the plateau will be much better, almost quantized at if you do electron or hot doping of this material. They are all measuring on the intrinsic material, and this is still not ideal. Yeah.
Okay, thank you very much.
Great, more questions? I have one short question. I think you have to go and teach soon, so I have a really short question. These Fermi arcs that you kind of show for these chiral multifold Weyl symmetries are very, very long, right? So they kind of extend throughout the entire Brillouin zone. And so in these Fermi arcs arise in these materials which break inversion, preserve time reversal symmetry, but no kill mirror as well, right? So we don't have head mirror. There's another kind of topological symmetal called a Dirac symmetal, and there's some ones which are called time reversal invariant momenta Dirac symmetals, which you have a Dirac cone at the time reversal invariant momentas. So I wonder, and in those systems there are actually no Fermi arcs. So I wonder in your system, if you break, if you then reintroduce the inversion symmetry, do you go back to these Dirac symmetals? And if so, what happens to the Fermi arcs? So if you now reintroduce inversion symmetry into your system, then you will preserve time reversal symmetry and inversion symmetry. So you can't have any more Weyl symmetal. So the Weyl nodes will die. But what's the evolution like? Do you go back to Dirac, or do you go to something else entirely different?
So because now we have, if we think about the simple case, we will have positive wire and negative wire here, right?
Mm-hmm.
So if you considering this band structure, it's not a simple, it's not a small perturbation. You need a huge change of the band structure, which probably would destroy the wire fermion. And
yes, so of course you will kill the Weyl fermions when you have both time reversal symmetry and inversion symmetry. That's true, of course. But my question is it possible to understand the evolution of these Fermi arcs, which kind of traverse the entire Brillouin zone, right? They kind of go everywhere. So you know, we know in Dirac symmetals, unless you're in the special case of topological Dirac symmetal, you have no Fermi arcs.
Yeah, so maybe the most naive thinking is you will have another pair of wire fermion, and maybe the Fermi arc will connect in this way, and you put them together in one figure, you will see some structure like this. So besides this part, there will be another part here.
I
so
see.
similar here from here. This would be similar to Su Yang's measurements in NA3BI, but I'm not sure. This is my naive thinking.
Yeah, but in that system, he breaks time reversal symmetry, right?
NA3BI didn't break time reversal. It's still it's just 3D Dirac system.
Oh, sorry, yes. No, not the recent work. Sorry. Yeah. Okay, good.
Yeah.
All right. Thank you very much. More questions? If there are no more questions, let's thank Guoqing for this very interesting talk. Lots of new results. Thanks a lot.
Thank you.
Okay. Bye.
Bye.
So Chang, you can stop the recording.